Albert Einstein, the name conjures images of wild hair, a chalkboard scrawled with E equals mc squared, and the genius who redefined gravity. But behind the icon lies a far more complex story, one of a man who witnessed the quantum revolution only to spend decades fighting against its consequences. This is the tale of a visionary trapped by his own brilliance, a skeptic who challenged reality itself, and the ironies that made him both the fiercest critic of quantum physics. Our story begins in 1905, Einstein's miracle year. While best known for relativity, it was his paper on the photoelectric effect that secretly planted the seed of quantum chaos. Scientists were baffled. Why did ultraviolet light eject electrons from metal while even intense red light failed? Einstein's radical answer? Light itself is quantized. Imagine waves crashing on a beach, but instead of water, each ripple is a particle, a photon, packing energy proportional to its frequency. E equals h nu. This defied 200 years of light as wave dogma. Even Max Planck, whose constant h made the math work, called it a desperate act. Yet experiments proved Einstein right, earning him the 1921 Nobel Prize, and unwittingly birthing the quantum era. But Einstein's quantum journey didn't stop there. His work on wave-particle duality for light inspired others like de Broglie to extend it to duals, suggesting electrons too could behave as waves. He collaborated with Satindra Bose to create Bose-Einstein statistics, predicting exotic states of matter that wouldn't be observed until 1995. Paradoxically, these contributions fueled the very theory he'd later reject. By the 1920s, quantum mechanics, QM, had become a wild beast. Heisenberg's uncertainty principle denied precise knowledge, Schrödinger's equations dealt in probabilities, and Bohr's Copenhagen interpretation declared reality is what you measure. Here the conflict ignites. Einstein, the man who demolished Newtonian absolutes, couldn't stomach quantum randomness. God does not play dice with the universe, he declared. To him, probabilities were a crutch, a sign that QM was spooky, missing hidden variables that restored determinism. In 1935, he struck back with the EPR paradox, a thought experiment so devious it seemed to break physics itself. Imagine two entangled particles. Measure one spin and the other spin instantly chooses a state, even light years away. This spooky action at a distance violated Einstein's belief in locality, no faster-than-light influences. His goal? To expose QM's flaws. But in a twist worthy of Greek tragedy, later experiments confirmed entanglement. The paradox meant to kill quantum theory instead became its crown jewel. Through it all, Einstein waged a decades-long intellectual duel with Niels Bohr, the quantum pioneer. Their debates were less about equations than the age-old questions. Bohr accepted QM as the final word. Einstein demanded deeper truths. "Do you really believe the moon exists only when you look at it?" he quipped. Yet even in opposition, his critiques forced quantum theory to mature. Like a sculptor chiseling marble, Einstein's doubts carved away ambiguities, pushing physicists to clarify interpretations and devise new tests. So was Einstein wrong? Yes and no. The universe is probabilistic, and spooky entanglement underpins quantum computing today. But his insistence on seeking a grander framework lives on in the quest for quantum gravity. In the end, Einstein's quantum story is one of beautiful contradiction, a reluctant revolutionary who couldn't embrace his own revolution, yet whose doubts became its proving ground. As we peel back the layers of this saga, we'll explore how one man's battle with uncertainty reshaped our understanding of existence itself, and why, in the quantum realm, even geniuses must surrender to the dice. So, where did Einstein's defiance leave him? Trapped between the rock of experimental proof and the hard place of his unshakable conviction. The spooky action he'd weaponized against quantum theory didn't fade into obscurity. It became a siren call for a new generation of physicists. While Einstein retreated into his decades-long quest for a unified field theory, a deterministic cosmos governed by elegant classical-like equations, The quantum revolution charged ahead, fueled by the very paradox he had unleashed. His EPR thought experiment wasn't a death knell. It was a gauntlet thrown, demanding a deeper interrogation of reality. And science answered. Enter John Bell, a brilliant Irish physicist working quietly at CERN in the 1960s. Where others saw philosophical deadlock, Bell saw a mathematical chink in the armor. His Bell's theorem was a thunderclap. It proved Einstein's cherished concepts of locality, no instant influences, and realism, definite properties exist before measurement. Crucially, Bell provided a way to test it experimentally, a way to force reality to declare its allegiance. Suddenly, the abstract duel between Einstein and Bohr moved from the seminar room to the laboratory bench. Could the universe truly be as weird as quantum mechanics suggested, or was Einstein's hidden variable dream possible? The experiments began. John Clauser in the early 1970s built the first apparatus to test Bell's inequalities. His results leaned towards the quantum view, but doubts lingered. Then came Alain Aspect in France during the 1980s. His team executed experiments of breathtaking ingenuity, using rapidly switching detectors to close potential loopholes Einstein might have exploited. Lasers fired photons through intricate setups, their entangled fates measured across meters of lab space. The verdict? Aspect's results and countless rigorous replications since delivered a knockout blow. Quantum mechanics was correct. Entanglement was real. Non-locality was undeniable. The particles communicate instantly, defying Einstein's speed of light limit. God, it seemed, played dice, and the dice were loaded with spooky connections. This was Einstein's profound, personal paradox writ large. The man who demanded empirical proof above all else found his deepest intuition overturned by it. His critique, born of a desire to restore cosmic order, instead cemented the foundation of quantum weirdness. Yet, dismissing Einstein as simply wrong misses the staggering depth of his legacy. His relentless skepticism, embodied in EPR and his lifelong debates, wasn't obstruction, it was essential refinement. By forcing Bohr and his followers to rigorously defend every implication, Einstein compelled quantum theory to grow stronger, sharper, and more experimentally robust. He demanded answers to questions others were content to ignore. These weren't idle musings. They became the bedrock of quantum information science. Even in his failure, Einstein's vision echoes. His quest for a deeper deterministic reality, free from probability's grip, lives on in the search for quantum gravity and theories like string theory. Physicists probing the event horizons of black holes or the first moments of the Big Bang grapple with reconciling quantum uncertainty with the smooth fabric of space-time Einstein described. And the spooky entanglement he despised? It's the engine of the quantum computing revolution and ultra-secure quantum cryptography, technologies emerging from the principles he fought so hard against. The ultimate irony? Einstein, the reluctant quantum father and its most formidable critic, remains indispensable to its story. His resistance wasn't the end of the journey. It was the crucible that forged a deeper, stranger, and infinitely more powerful understanding of the universe's quantum heart. His doubts, once seen as stubbornness, are now recognized as the arduous path towards a truth far wilder than even he could imagine.
So, Einstein's defiance forged quantum mechanics into a titan of predictive power, yet the deepest cadences of his quest resonate louder than ever. The universe, it turns out, profoundly quantum, entangled, probabilistic, and astonishingly non-local. But Einstein's ghost still walks the corridors of physics, whispering a haunting refrain. Quantum mechanics, for all its triumphs over EPR and beyond, remains locked in a cosmic standoff with his other monumental creation, general relativity. Near the crushing gravity of a black hole singularity, or in the searing crucible of the Big Bang's first moments, where space-time warps beyond recognition, the smooth, deterministic geometry Einstein described clashes violently with the probabilistic, granular frenzy of the quantum world. Neither theory yields, both break down. This isn't just a theoretical nicety, it's a fundamental crack in our understanding of reality's foundation, screaming for the very kind of unified field theory Einstein pursued relentlessly in his later years. His dream of a single, elegant framework governing wasn't folly, it was prophecy. The search for quantum gravity, the holy grail of unifying these giants, is where Einstein's spirit is most palpably alive. Physicists wrestle with mind-bending contenders, string theory, weaving reality from vibrating multidimensional filaments, loop quantum gravity, quantizing space-time itself into a fabric of tiny woven loops. Each approach carries echoes of Einstein's core demands: mathematical beauty, determinism, and a universe where God does not play dice. Yet the path is fiendishly difficult. These theories operate at energies far beyond our current particle colliders, dwelling in realms observable only through their faintest cosmic fingerprints, the afterglow of the Big Bang, the ripples in space-time from colliding black holes. Testing them requires Einsteinian audacity blended with quantum ingenuity. And still, the core philosophical tension he identified persists. Does reality exist independently of observation? The measurement problem, the unsettling question of how and quantum possibilities collapse into definite outcomes, remains unresolved, fueling fierce debates between interpretations like the many worlds hypothesis, where every possibility branches into a new universe, and objective collapse models. Einstein's demand for a truly objective, observer-independent reality is far from settled. Yet, from this crucible of unresolved theory springs astonishing practical fruit bearing the ironic stamp of Einstein's resistance. The spooky action at a distance he railed against is now the bedrock of the second quantum revolution. Quantum computers, leveraging entanglement and superposition, promise to solve problems intractable for classical machines, designing complex molecules, revolutionizing material science, cracking current encryption. Quantum cryptography, using entangled photons, creates theoretically unhackable communication channels, securing data with the fundamental laws of physics. Quantum sensors peer into the fabric of space-time with unprecedented precision, hunting for dark matter or mapping underground resources. This technological leap is the ultimate testament to Einstein's paradoxical legacy. His profound unease with quantum theory forced its exploration to such depths that we now harness its weirdness as a tool. His skepticism didn't kill the quantum dream, it compelled us to master it. Einstein's journey, from reluctant quantum pioneer to its most formidable critic and ultimately its most influential philosophical provocateur, teaches us that science thrives not just on answers, but on the courage to question even its most successful paradigms. His stubborn refusal to accept quantum mechanics as complete wasn't a failure. It was a relentless demand for a deeper harmony, a grander symphony that might unite the quantum and the cosmic. Today, as physicists peer into black holes, simulate the universe's birth on quantum circuits, and chase elusive gravitons, they walk a path illuminated by his insatiable curiosity and uncompromising rigor. The contradictions Einstein embodied, the revolutionary who became the critic, the man who reshaped physics yet felt isolated by its direction, mirror the universe's own enigmatic duality. His legacy is not a closed book, but an open question, a resonant chord that continues to vibrate through every experiment probing the quantum void and the cosmic expanse. The symphony remains unfinished, and Einstein's voice, forever challenging, forever seeking, remains its most profound and enduring counterpoint.